My name is Pat Quillen. I'm from the MathWorks. I would like to, thank the organizers for having us today. I'd also like to thank Mike Haru for pushing us to organize this mini symposium to come talk about the things that we do, making MKL, making MATLAB, and making, the CUDA math libraries. So thank you very much to Mike. I'm here today to talk about what we do at MathWorks in trying to develop libraries to support multi-core hardware. Lots of our customers have this kind of hardware, and they expect decent performance. So let's go ahead and get going. So at its heart, MATLAB fundamentally is about productivity. When Cleve Moeller invented MATLAB in the 70s and the 80s, it was about making an environment where his students could play with matrix computations without really having to worry about writing Fortran. That is still true today, and in fact, it's true to a much greater extent, I think, especially because it's not just Fortran on a single core CPU anymore. It's multi-core CPUs, GPUs, clouds full of processors, farms of GPUs, FPGAs, and the whole 9 yards. Now, while at MathWorks we have tools for a lot of those things, and we want people to be able to run MATLAB code credibly on those kinds of processors, mostly we think about machines just like this. So our users use MATLAB on a variety of machines. Maybe not anything as archaic as the thing there on your left, although it does feel like that sometimes. But fundamentally, we have users using MATLAB on 2, 4-core laptops and desktops that can be a decade old. Some number of years ago, maybe it was 7 years ago. No, we finally dropped support for Pentium 3, and we had users who did not like that, which is utterly remarkable, but it's a fact of life. We have other users, on the other hand, who want to run on 32 core machines, 64 plus core machines, and treat that as running. They want to run MATLAB as a single process on that kind of machine. And the bottom line is that fundamentally, our users expect good machine-appropriate performance, okay, in MATLAB. All right. So what that means for us as developers is that we can't really assume too much about the machine, right? We can assume it's x86 64, that's all we support anymore, but we can't necessarily assume that it's AVX, AVX2, or anything special like that. Maybe it's simply SSE2. We can't assume much about the memory of the machine. Maybe it has 4 NUMA nodes that are massive. Maybe it's just a 4 gigabyte memory machine. Yes, I have users who do that. Maybe the users can use the whole machine, or increasingly likely, it's a 32-core machine that is shared among multiple people who are whacking on MATLAB simultaneously on the machine. And still, people want reasonable performance in that environment. So one of our big strategies has been to, let's use multi-core enabled third-party libraries, right? So here, this is, I'm showing you a screenshot from the year 2000. This article was published in 2000 about how MATLAB incorporates LAPACK. That is still true. We're using LAPACK, we're using BLAS, but more than that, we're using vendor-optimized versions of that where we can. In particular, we make use of Intel MKL, and one of the things that Intel MKL allows us to do is keep not assuming things, right? Where MKL is able to runtime dispatch to AVX2 enabled versions of, say, GEM, if the machine has AVX2, and that makes our users happy. Also, Intel MKL and other libraries like it not only have instruction level parallelism via SIMD, but they provide usually OpenMP threaded versions, and those versions have been very effective for us and for our tools. On the other real big strategy, though, and again, this is nothing new, right? This is not rocket science. It's just a thing that we've applied very effectively. Write your algorithms in terms of kernels or tasks, right? Thread those kernels individually, optimize those kernels individually, and you can achieve very good and relatively portable performance. A thing that has been very, very effective for us, in addition to using third-party libraries like MKL, implementations of LAPACK and BLAS, are in particular Intel threading building blocks. It's been a library that has been very, very effective for us. It fits a lot of our requirements, which are don't assume much, right? The work stealing scheduler helps in situations where we have high core counts and low core counts. It's a standard C++ library. Now, unlike OpenMP, I don't think TBB is a standard per se, but the library is implemented in, I think, C++ 11. So it's a standard C++ library. But the key thing for us is really the composability. TBB was designed with composability in mind, and so we can thread at every level and nest those things together and not suffer too much. Okay? So now, it being towards the middle of February, I will go ahead and publicly, profess my love for TBB. It's a library that's been very effective for us, and I do love it. So I want to talk just a little bit about some examples. These days, convolutional neural networks are a very big deal. I am not a deep learning guy. My co-author, Chris, who did a lot of this work, also, he is not a deep learning guy. I see the world as basically being all sparse matrix multiplies. He sees the world as being all convolution, so he's closer. But fundamentally, that's not who we are. That said, these kinds of techniques are increasingly important to users of MATLAB and technical computing tools. So let's talk just a little bit about what these things are. So the kinds of computational neural networks or convolutional neural networks that we're looking at are essentially things like AlexNet, ResNet, GoogleNet, and many others just like it. Mostly, we are interested in things for image classification, and these things kind of take an image in one end, pump it through a bunch of layers that convolve, activate, matrix multiply, which is also known as a fully connected layer, things like this, and then spit out at the other end some classification. The particular silly picture I have here is classifying each pixel in a given image, but you can also classify images as, oh, that's a picture of an owl, or oh, that's my third grade math teacher. The point is that some of the layers are computationally heavy, some are less so. So there's opportunities to leverage multicore at the layer level and then also at the whole network level. In MATLAB and MathWorks tools, deep learning essentially starts on the CPU, right? Many people, when they hear deep learning, they think, oh, it's GPU time, let's go. And essentially, like, the state of the art is fundamentally, training on GPUs, using GPUs for inference, having specialized kinds of GPU type cards in your vehicle to do automated driving type exercises. But again, for many, many, many of our users, deep learning starts on the CPU, and that's a place where we want to facilitate that kind of interactive and explorative work. All right, here's a screenshot of something called the Deep Network Designer, which is an app we have where people can import, design, tinker with CNNs. You can write your own custom layers. You can use some of the library of layers that we have here, hook them together into a network, train them, and do inference. You can also use GPUs. We have tools to push out to leverage a GPU right in the confines of an interactive MATLAB session. We also have tools that can take those neural nets and deploy them to standalone C code to be deployed. Some users, though, in fact, I would argue many users, never leave the desktop. So it's, again, critical for us to provide good, machine-appropriate, kind of not terrible performance. So I'm about to show you some numbers. Now, the absolute numbers are nowhere near state-of-the-art, okay? So I know that, I'm aware. I'm not standing here telling you that MATLAB has the best deep learning performance. That's not the point. The point is about the evolution of how we're improving and exploiting multicore better. So here's the evolution of the prediction performance for ResNet 50 from release 2018A to 2018B, right? So we got about a 30% bump. And so all the numbers, by the way, are taken off of an Intel Xeon E5-1650, which is pretty reflective of the kind of machines our users use. That's pretty reflective of the kind of machine that we develop on. The way we got that, say, 35% increase is, in this case, using better convolution strategies. We're taking TBB and we're wrapping gem calls, we're wrapping AXPI calls, we're doing things like that. We're doing elementary layer fusion, so some of the activations that follow convolutions. So very frequently in these networks, you have a convolution followed by a ReLU. A ReLU is simply max of yourself and 0, so it clips you at 0. Doing that in one pass instead of kind of going back out to MATLAB and coming back in really got us some performance. And also we have an improved TBB versions of pooling and things like that. At this level, at the layer per layer level, what we're doing is effectively just using TBB parallel 4, TBB parallel invoke. It could have been OpenMP, right? But I've already told you about how I love TBB rather unabashedly. Then we went to the next release, because we're always working. We have many things to do. And you see the improvement was not that substantial, maybe 8%, maybe 10%. And here, this is where we started again. We constrained ourselves still to, individual layer tinkering, right? We tried to reduce data copies where we could. We reduced data permutations. And there we actually threaded permutations, we threaded copies, we threaded fills. The point is we found some fruit in threading these things that would be basically akin to what you would think a level 1 BLAS is, right? So here we have kind of this layered approach to implementing our layers. We're threading at the lower level, we're threading at the layer level, we're trying to get as much throughput as we possibly can. But again, if you think that way, you're introducing sync points, right? The sync points between layers. And those sync points are going to limit your parallelism, right? So you can see here, this is essentially a DAG. And so what we did next is try to move up a level and do some parallelism at a higher level, again, using TBB. And we got quite a bit of performance boost. Again, these are not best-in-class numbers, but now we've gone from being about 2.5 orders of magnitude slower than best-in-class to just about 1.5 orders of magnitude. So remember, this is in MATLAB on a desktop class machine. The way we did this is actually we did whole network execution using a TBB flow graph. So this is a little bit more of an advanced TBB API. And what we've done is we've taken the implementations of the layers and actually we've convinced them that they are TBB nodes in a TBB flow graph, and then we just pump the whole thing through TBB. So you take your network, you make an object, and then essentially push play. Now, in none of this have I told you about any kind of scaling. So here again, this is the 19B number. This is speed up of 6 cores over 1 core, right? So again, not wonderful, but we're getting about 5.25, maybe 5.5x at the 32 batch size. This is the kind of compute utilization that our customers are expecting. Our customers do expect linear speed up with number of cores, which is irrational, but they expect it. I think everyone expects it. Sometimes we give them super linear, but that's because we make other improvements. But here we're doing a fairly decent job. On the low end, it's about 3.25 up to about 5.5. And again, what we've done here is we didn't just work on ResNet. These kinds of results extend to the other networks, because again, we essentially built a pile of building blocks on the inside and then hook them together in a TBB flow graph and let TBB have it. So these are the results for AlexNet, which is another very popular neural net. And what you see here is AlexNet got the same kind of giant boost with the purple bar going up to 2019B. The absolute number is a little bit better, but still we're not best in class. Also, you see about a 4 3/4 speed up at the batch size of 32. So wrapping it up, I mean, here, the point really is that, I have a lot of users who are using MATLAB in various computational environments, and I don't have a lot of assumptions about what the machine looks like. And so what we've been successful doing or is using Multicore at every level, and we found that to bear quite a lot of fruit. And for us, composability is key, right? So not having to worry about whether or not a gem is threaded or whatnot, and letting the runtime just take care of it has been very, very useful for us. Some of the future work where we can make more improvements, we can introduce pipelining that's already kind of shown quite a lot of fruit for us, but it's not quite cooked. And then also, I had told you some of these layers can be completely custom authored MATLAB. It can be really literally whatever MATLAB you want. And so trying to make our framework robust to that is something that we're looking forward to in the future. So, thank you very much.